Okay, we're going to take a look at the idea of a latch. All right, let's just say that we have some sort of a pendulum-like device. Okay, so there's a swivel point right here, and the pendulum can swing from this point to that point. All right, and you can just swivel freely as it goes. Let's just take a scenario like this. All right, let's just take this as a resting point. And let's say that this is some sort of a strong magnet. Okay, now we're talking about a latch, so we're missing something. Let's just get a couple of latching like devices. So let's say this is some sort of a spring-loaded kind of a device here, and some sort of a spring-loaded device kind of with a spring, and it's going to latch onto things. So once we bring it here, it's going to click and it's going to stay there. All right, and if we will bring this thing here, it's going to click and it's going to stay here. All right, so let's just say we're going to bring a strong magnet that is going to attract this end of this stick here. Okay, so once we bring it here, that stick is going to move right here and it's going to stay there because it's going to click on here. Now it doesn't matter where we move the magnet here or that way, how many times we're going to move it to this position, that thing stays there. All right, so it latches into this position. Now let's just say that we're going to take the magnet and move it from this point to this point here, and that is going to make that move that way. All right, and it's going to stay, and then doesn't matter how many times we're going to put that here, it's staying there. So that's the idea of a latch. All right, so here it's going to come over there and it's going to latch onto things and it's going to stay there. And then doesn't matter how many times more we're going to apply this motion, it's going to stay in this position, same as the other position. As soon as we take that magnet and bring it to here, it's going to stay here. Now let's see what the conditions we have. All right, now when we have the magnet somewhere, the magnet disappears, so there is no force applied here, there is no force applied here. So let's say when we bring the magnet to this position, this one becomes logic 1. All right, so we got logic 1 here, this thing moves here, and it doesn't matter how many times we activate this point, how many times we go bring it from 0 to 1, this little pendulum device is going to be latched onto this position. All right, and then when we go and apply the logic 1 instead of here, because once we move it, that becomes 0. All right, and these are both zeros, so that means this is a latched position. Okay, now once we apply the logic 1 here, then bang, this thing is going to come here and it's going to stay here. And it doesn't matter how much we're going to make it 1 or 0, it stays there. All right, now there's also an invalid state because you only have one magnet. All right, we cannot bring this magnet into both sides at the same time, so this is going to be called an invalid state. It's just impossible to accomplish. It just doesn't exist. All right, okay, so now when we have that idea out of the way, let's just take a look at some electronic representation of this thing. I'm just going to switch some screens here and over here. Now this is a multi-sim screen that we have. Let's just see what we have here. Now if we arranged two NOR gates, right, so it's an OR gate with an inversion bubble, so that means it's a NOR gate. So if we arrange two NOR gates in this sort of a way, we are going to create something that's called a latch, just like the one that we were operating with the let's say swivel device that we were doing. Okay, so the same idea. Right, now the inputs here, one of the input, the far input, we're going to call it R for reset. The other input that's far, we're going to call it S for set. All right, so here's a set and reset. RS latch made out of NOR gates. All right, now the output of the first gate we're going to feed back onto the other input of this bottom NOR gate, and the output of this one we're going to feed back onto the other input of this top NOR gate. If we arrange this these two NOR gates in this way, we're going to come up with something like this. That's a truth table of that. Now the outputs of that So now we have the whole those two NOR gates assembled into one device that we're going to call it a latch. Okay, so this is our RS latch. This whole arrangement is called a latch, made out of NOR gates. Okay. Now this device has two inputs and it has two outputs. Right. Now when we talked about the multivibrators, which kind of multivibrator would this be? All right, is it a monostable, is it astable, or is it bistable device? Well, basically what we can say is that it has two valid states. The output can either be here, that stick can swivel from the middle to here, or it can go here. Right? It's just like the stick was swiveling from Q to not Q. And that, as this suggests here, whatever the Q is, it could be in digital electronics would be 1 or 0, logic 1 or logic 0, and this not Q is just the opposite. So if this one is 1, this is going to be 0. If this is 1, that is going to be 0. So they will never be both the same, because we only had that one stick and we could only swivel this one way or the other. So if it's one way, it's not there, and if it's there, it's not here. Okay. So now let's take a look at this truth table here. So we have the R and S over here. And what can we have? We only have two inputs, so we can have 1, 2, 3, 4 possibilities. We could have both of them at 0. We could have the possibility of one being momentary, one of them being momentary. So remember we just applied that little magnet only to one position, or we can apply it to the other position. And then here, because we only have one of that, we only have one magnet, then we wouldn't be able to put that at both places at the same time, so that is called an invalid state. I'm just translating this truth table. So instead of looking at the truth table and trying to remember, if this is that, then this is latch, and trying to remember this thing, that's not a very good way of comprehending things. So let's translate this thing into something that is you can associate it with some idea, and the idea is a latching device. All right. So again, so if we have one of them momentarily at 1, so if the S is going to become 1, then you could see that the Q is going to become 1. So if we apply logic 1, 5 volts, for example, to this one, and the other one's going to be 0, because we can only move it either this way or that way, or to none. Okay. So so here is the representation of that, and we can't have them both at the same time as 1. All right, that's an invalid state. Okay. So the latch works on pulses in such a way that, for example, if we apply a pulse, which is a momentary 1 at the S input right here, then the Q output is going to latch. It's going to move into 1. And then, of course, because it's a momentary condition here, we're going to divert back to this position here. So this is basically latch is almost like a resting point for the latch. So we're sitting at both zeros, and sometimes we'll bring this one to 1 and come back, or that one to 1 and come back. And if we bring this S to 1 and the R is the set to 1 and the reset is to 0, the latch is going to give us this result. Q is going to become 1, and the not Q, of course, is going to become 0. And then when we go back, nothing is going to change. So it's going to, sometimes it's going to be listed as previous state. All right, so it's the same thing. It's going to latch onto that. So we bring 1 and come back to 0, and it's going to stay that way until we apply the input of logic 1 to the other input. So things are going to switch, and they're going to stay when we come back to 0. So it doesn't matter how many times we're going to put 1 and 1 and 1, it's going to stay that way. All right. So now let's just turn on the multi-sim simulation here and see if whatever I said is true. All right. So we have the truth table of the latch, the SR or RS latch. The input, they're active high. this is an RS latch made out of NOR gates, and in this case the input is going to be active high, and it's going to react to the positive edge. So it's positive edge triggered multivibrator, positive edge triggered bistable multivibrator. Okay, multivibrator is a device that switches from 1 to 0. Okay, now astable multivibrator is one that it doesn't require any triggers. Once it's turned on, it oscillates from 1 to 0 all the time. Okay, so that's astable. It doesn't have any valid or stable conditions. Once it's turned on, it just vibrates from one to the other, from one to the other. All right. Now the monostable would be if there was one output condition that is set to be at rest, if you will. All right. So if we applied momentary, if this was monostable multivibrator, then if we applied one momentary, came back to 0, this condition would be only valid while this 1 is applied. When we go back to 0, this output state would go back to whatever it's set to be at rest. So it's not a monostable multivibrator. This one is a bistable multivibrator, because once we set this thing up here, it stays there and it's considered to be at rest at that moment until we change the conditions certain way that we apply the logic 1 to the other input, and then it switches to another valid state. So it has two valid states. We can make it go to one state or the other and make it stay there. So it's a bistable multivibrator, active high because we're applying ones. So the inputs are normally sitting at 0, and we are activating it by giving it high condition, or one or the other. So it's active high, positive edged. Because, why is it positive edge triggered? Because it only reacts when we change this input from 0 to 1. Okay? So when we change it to 0, so the pulse goes from low to high, then this device reacts. All right? When we go back from high to low, it is not going to react. It's going to stay as it's going to stay latched when at the position that we made it to go to. All right? So what do we have? Over here, I have assembled two NOR gates in this very way here, connecting these two NOR gates in this arrangement like this here. Right? So the Q over here, we're going to label this as Q. These are just the probes, all right, indicating high or low. If the probe is lit up, that means it's a logic high. If the probe is not lit, then it's the logic level of low or 0. Okay, and the not Q, of course, is this one here, right here. So that is just indicating the condition of the Q or not Q. And at this point, the simulation is not on, so it's just whatever it was and just stay that way. So at this point, you can say that the Q is not on and the not Q is on. And it can only reverse. They can never be both 0. They can never be both high. Okay, one and the other. Or the other only goes high. All right. Now I have installed a couple of probes here just to monitor the condition of this NOR gate, and these are the couple of the probes here just to monitor the input condition of this. Let's just analyze this thing. How is it? Okay, here's the truth table of the NOR gate. Okay, so 0, 0 gives you 1. Anything else will give you 0. Okay. If it was OR gate, this whole thing would be reversed. It would be 0, 0, 1, 1, 1, 1. All right, but now it's because it's an inversion bubble. It's the inverted version of an OR gate. Okay, so here's the truth table. All right, so let's just analyze that. 1 and 1. So if it was OR gate, it would be either one of these two. If it goes high, the output would be high, but because we have the inversion bubble here, that high becomes low, so we have a low here. Good. All right, now we have the only condition of the NOR gate is if both are 0, then we're going to have a logic level of high or 1. So yes, this one here is low and this one here is low. Yes, of course, we're going to get this condition right here on this other gate. Okay, now over here I just have some, that's called a pull-up system of the resistors. So here's a VCC, and VCC we tapped on at 5.0 volts, so that's good. and there are just some current limiting resistors. So we go the current pathway for this input. So you see that point here is connected to this input right here. Okay, it's this one. It's the R for reset, and that's the one here. Okay? Now the other one, S for set. This input is connected to that. So if we have the switch open at this point is not connected to ground directly. It is just it actually sees the VCC through that resistor, so it's going to be pulled up high. So when the switch is open, the system is, this point here is high. If we close the switch, all right, actually this is a running system here. We close the switch, then this point becomes 0. Let's check it out. This is ground, connected to ground. Okay, so that is 0 here. All right, and it continues that way and continues that way. Yes, it's connected to this probe right here, and this probe is 0. All right, so what do we have, what condition do we have at R and S, reset and set, or set and reset? The R is 0, and we have the probe suggesting that this is 0. That's good. And the S is 0. So let's see the truth table of this latch. 0, 0, and it's latched. So it's going to keep the previous state. All right. So no matter how many times I open and close the switch, which means no matter how many times I'm going to make that R 1 or 0, that previous state of the output is not going to change. But what's going to happen if I operate the other one, which means I'm going to apply the logic level 1 here. So we're going to go to 1 to the set. Let's see, set 1 and the reset 0. We're going to have the Q1 and not Q0. So things are going to reverse here. So let's make this one go high momentarily. All right. So I'm going to open that, make it high. Watch these outputs. There we go. All right, so this thing has, now no matter how many times I'm going to operate that switch, all right, that thing is going to stay high until I change. It's a momentary, it should be momentarily only operated. So we got open and close. All right, we've opened and closed the other one. The condition is going to change. Open and close. All right, and no matter how many times we're going to operate that switch, things are going to not change right here. See, I'm opening and closing, applying 1 or 0. Now I'm going to go back to the latched state. I'm going to operate this one now, and we're going to have a momentary high here, momentary set high. So things are going to trigger the Q to be high and the not Q to be 0. Right? And then no matter how many times I'm going to activate that switch, things are going to stay. So it's a latching system. We can latch this onto reset state. All right, I'm pressing and pressing, or we can latching it into set state. All right. All right. So now, does it remind you anything? Remember what a switch bouncing is? If you operate a mechanical switch, it opens and closes in a very short period of time. It just bounces like a spring-loaded bounce. And we are not going to change the conditions. We're going to have a clean output on that. Same as if you're going to operate that now. All right. All right. Doesn't matter how many times I open that. This thing is going to stay. And or I'm going to operate that one. All right. And this thing is going to stay here. Okay. So this here is an idea of a RS latch made out of NOR gates. And if the RS latch is made out of NOR gates, the system is going to be active high, which means it's going to rest at 0, or being latched at 0, or keep the previous state at both 0, at whatever it is, when these both inputs are 0. When one of the inputs momentarily goes high, then it's going to behave according to this part of this truth table, and it's going to stay that until the other input is momentarily activated. But this is when we use 2 NOR gates. All right. Now, I would encourage you to go and jump on the multisim in our homework, one of the homework labs, or the open lab room, fire up the multi-sim, watch my previous video on how to place the components and assemble that circuit this way, but you can do it with NOR gates and repeat what I just did. The only thing is I'm going to encourage you to see what I did here. I'm going to stop the simulation. If I right click on this probe and I call up the properties, all right, and here is the label. The label is X7, but it's not being displayed because when I click on display here, I just turn all the displays off. If I just show the labels or values, or this one actually is the show reference descriptions, it's going to show X7. But I just, for the clarity purposes, I just turned all the displays off so we could see things clearly without being polluted with all the labels. Now, I was getting very frustrated with multisim because as soon as I labeled that as Q, then the whole thing just wouldn't work. For whatever reason it is, it's probably some sort of a software glitch or who knows what that is. So just when you bring up the probes, let them be labeled as they are, and then you can play with the labeling. Now this Q here, I just put it as a text. All right, so you can go place text. All right, so I just placed a plain text and I brought it right to here. All right, so that's just advice on how to use that, and you can probably repeat the condition that if you name a Q instead of X7 or whatever X is going to give you, then the whole thing is not going to work as it should. All right, or now I'm going to encourage you to use the other arrangement of the RS latch. Instead of using the NOR gates, plug in, instead of these NOR gates, do it with the NAND gates, and you can just figure out whether this thing is still going to be active high or is it going to be still positive edge triggered. It is going to be, it's going to work as it should, but the input is going to be provided in a different way. All right. Okay, so that's as far as the multi-sim version of that. Now what I have also, I have set up here a real version of this. Okay, so this is what is that, 7402 NAND, NOR gate. So whatever it was on that schematic, basically I repeated that here on the breadboard. So here we have the positive rail red, and I brought it up to here just so we have the positive rails here, and we have negative rail here. So over here, this wire is basically set up to the power supply right here to the 5 volts. Okay, so now what I have here is the Q, and the not Q is here. And instead of having switches, I didn't have any push button switches, so I'm going to simulate the switch with the wire. So they are both brought to low. So here is the set, here is the reset. They are both brought to low. So when I remove that wire, if you look at the schematic that we have, it's a pull-up system. If I remove that wire, I'm going to disconnect the ground for that from that input point, and through these resistors, this input, one of the inputs of this NOR gate, there are 2 NOR gates. There's one NOR gate here, and there's the other NOR gate, and it's arranged like input, input, output, and here is input, input, and output. Okay, so you can figure that out, or you can just get the data sheets and get the schematic of that. Now, when I remove that wire from ground, that means this point is going to become high, and this is connected to, see, one of the inputs here. All right, and then this cross connect feeding back. One output is connected to the other input, and the other output is connected to the other input from the other gates. Just look at the schematic. This is the way it's assembled. Okay, and this 7402 is the TTL device here, TTL logic chip. Okay, and this is quadruple NOR gate. So it has 1, 2, 3, and 4 NOR gates. We are using 2 of them, and the other ones are not used. And of course, we have, it has to be powered. Okay, so see that here, this pin 14 is powered up, goes to the VCC, and this pin 7 goes to the ground. All right, so if we don't have that, it's not going to work. It's just like the television set. You can change the channels with the remote control all you want, and you can feed all kinds of signal all you want, but if that TV is not turned on, it's not going to display anything, right? So it's the same thing here. You have to turn that device on by providing the power to it. Okay, so this thing is powered, and now it's going to work as it should when according to the truth tables of the NOR gates. All right, so we have a Q and not Q, so obviously we have this thing in that way here. Now this is the set, this is the reset. So if I momentarily make this one high, the condition should change. Let's see if it's going to happen. Okay. Oh wow! And now it doesn't matter how many times I'm going to make it low. All right, I can just keep switching this thing on and off. It stays that way. All right. So let's just leave it at the latched. It's a resting position here, and I'm going to do the other one, the reset. I'm going to momentarily make it high by removing the ground from that point, and this thing should switch. All right, it does. Oh, look at that. And then how many times, doesn't matter how many times I make it up and down, we just made it going one way until the other input changes. Okay, here and here. Okay, so that's basically the idea of the RS latch. It latches things. It keeps the memory on how it was set the previous time until the condition changes, telling it to go the other way. All right. Okay. See you next time, guys.